video, let's do a couple more examples of using this formula right here in order to calculate volume after we figure out cross-sectional area. So the first problem we'll look at in this video is the base of a solid is the disk. X squared plus y squared is less than or equal to 1. So let's draw that picture here. This is the base of our solid. And so now cross-sections perpendicular to the x-axis are triangles. So if I were to say, here's a point A and here's a point B, so the cross-section that is perpendicular to the x-axis, here's the x-axis, is a triangle that is coming off of the page. So it's a little bit difficult for me to explain what's going on here because it's hard for, video is a two-dimensional thing. You can't see me waving my arms as nicely around in 3 dimensions. But take this, if you can see my finger coming off of the page here, there is some triangle that is coming out of the circle. Okay, so, and not only it's not just any kind of triangle, but we're told, importantly, triangles whose base and height, so the base here and the height here, are equal. And so our job is to find the volume of the solid. So what we're going to do is that we're going to figure out a formula for the cross-section area, but instead of integrating respect to y, we're going to be integrating respect to x here along the x-axis. So what information do we have? Well, this point right here, let's say it's at a generic x point. So that's x comma, we'll fill in the y coordinate here. A generic x point on the circle x squared plus y squared is exactly equal to 1 is the y value square root of 1 minus x squared. And down here, b is at x comma minus square root of 1 minus x squared. Okay, so what do we have? What is from a to b, that's from here to here, that's square root of 1 minus x squared times square root of 1 minus x squared. So from a to b, this is going to be 2 times square root of 1 minus x squared. And moreover, we're told that the base and height have equal length. So this is also 2 times square root of 1 minus x squared. And so what do we have here? Area is equal to 1/2 times base times height. So that is 1/2 times the base is 2 times square root of 1 minus x squared times the height is also 2 times square root of 1 minus x squared. And so 1/2 cancels with a 2, and so we have 2 left over, and those square roots go away. So the area is just 2 times the square root of 1 minus x squared. That's the cross-sectional area with respect to x. Okay, so now we have to integrate. For integrating, x is going to run from -1 to 1. So we're going to integrate x is running from -1 to 1. The area, the cross-sectional area we just found with respect to 2x. And so this is going to give us our volume here is the integral from -1 to 1. A of x dx is the integral from -1 to 1 of 2 times 1 minus x squared dx. And this is a very straightforward integral to do. I'll skip the steps to evaluate this. You end up with 8/3 at the end of the day. So we don't have to calculate our cross-sectional area in terms of y. Sometimes we can do it with x. Sometimes that is going to be easier. Okay, so that is one problem. There's one more problem I want to do in this video set. And so here we go. The base of the solid is the region bounded by y is equal to x squared, and y squared is equal to x. So that looks like, let's draw a picture here. This is y squared is equal to x, and this is y is equal to x squared, and they intersect at the point 1, 1. Okay, so we're told there's a couple parts that we have to figure out here. So cross-sections perpendicular to the y-axis are equilateral triangles. So an equilateral triangle here is a triangle that has all sides having the same length, and the area of an equilateral triangle with side length L is square root of 3 over 4 times L. If you don't know how to do it, it's a good thing to derive yourself. You can do it by chopping, do a little bit of trig here. This is the angle right there is pi over 3, or 60 degrees, and that angle right there is pi over 6, 30 degrees. So a 30, 60, 90 triangle, we know lots of things about that. Okay, so if we find the side length, we'll be able to find the area of our equilateral triangles. Now let's read the problem carefully. Cross-sections perpendicular to the y-axis. So unlike in the previous problem, but similar to our pyramid problem, we're thinking our cross-sections in terms of the y perpendicular to the y-axis. We're going to be integrating from 0 to 1 along the y-axis. And so we're going to try to figure out what is this side length, not in terms of x, but in terms of y. Okay, so how do we do that? So y is equal to x squared. We could rewrite that as x is equal to the square root of y. And so in terms of what's going on here, this is from here to here. This is x is equal to square root y for a fixed y value. But then from here to here, this is y squared in terms of x in terms of a fixed y value. So what we're doing is that we're doing square root y minus y squared. Our side length is, the square is this minus that, is square root y minus y squared here. So our area is simply, and let me replace L with y here, is square root 3 over 4 times this side length, square root y minus y squared. This is the area that we have here. And by the way, I've made a mistake earlier. My apologies for not catching that earlier. I needed to square the side length. It makes sense that if this side length here is a one-dimensional thing, so to get area, we have to have a two-dimensional square the length here. So a of y is square root 3 over 4 times all of this squared. Okay, so to finish off this problem, we have to integrate this. We are integrating between, let me pull this back here, y is running from 0 to 1. And we are integrating the area in terms of y, which is square root 3 over 4 times square root y minus y squared, all of that squared dy. And so we can move out that square root 3 over 4, integral 0 to 1. If we expand this out, we get y minus 2 times y to the 5 halves plus y to the 4th dy. And this is a very straightforward integral to do. So once more, I'm going to say equals ... equals 9 times square root 3 over 280. It would be good if you wanted to do this at home to check to see that this is, in fact, the answer that you're supposed to get. Okay, so I think this is a good place to wrap up this video. And so here is our first pre-class problem for section 6.1. So the base of the solid is the region bounded by the curves. Y is equal to x squared minus 1, and y is equal to x1 minus x squared. Cross-sections perpendicular to the x-axis are squares. And so I want you to write down an integral that you could use, particular to this solid here, that would give you the appropriate volume. You don't need to evaluate it. You can stop at, like, this would be the appropriate place to stop in the previous problem. So please take a look at this pre-class problem.